All right, everybody, I'm going to make this a pretty short and sweet little video just so you can follow along. The good news is that there's only one extra little thing today that we're going to talk about that we haven't already talked about, and that is going to be how to graph lines. All right, so what I've done here is I've just made a PDF of our slideshow that we would normally do. Normally I'd have you do a bell work, but we're going to skip that today. Not super important. So what I want you to do is I want you to copy down these notes here as best as you can, or honestly, they're also on Google Classroom, the notes key. But let's go ahead and see what's going on. So as we talked about, a solution to a system is the location, or notice that could be locations, where graphs intersect. Okay, so, whoops, there we go. We can represent the system as a graph, equations, as table of values, although we're going to focus on just the graph and the equations. So the solution here, if we see where this green line crosses this black parabola, we can see that there are two locations where they intersect. And those locations are going to be the solutions. So when I write my solutions to this, I would write this ordered pair down here as -1, 1. And this ordered pair up here would be 2, 4. Okay. This happens when you have a parabola with a line. Not all solutions will be two ordered pairs. Okay. Now, if we were going to graph lines, we would want to first make sure that the equations are in slope-intercept form. So y equals mx plus b. Then we want to graph both lines and find the point where they cross. So if I look at this first example, example 2, we're going to graph y equals 3x minus 1. So our b in this case is -1, and we plot that on the y-axis. So it's our y-intercept, okay? So I'm going to plot the -1 here on the graph. And my slope is 3, which when we do this, you need a rise over run. So we're going to put that 3 over 1. And what we're going to do is from that point I plotted on the y-axis, I'm going to count up 3 and over 1. And if I find I can't go up 3 and over 1 anymore, I'm going to go down 3 and left 1. Because remember, down and left, that's two negative movements, which makes a positive. And then we connect them with a line. Okay? Now I'm going to do the same thing with the second equation, except the only difference on the second equation is I don't have y by itself. So I have to divide everything by 2, and that gives me y equals 2x plus 1. So my y-intercept is +1. My slope, I'm going to put that as 2 over 1. I'm going to go up 2 and over 1, up 2 over 1, and I can see now that I'm going to have a point of overlap. Okay, so now I have my ability to write our solution, and we're only going to have the one, and it occurs at 2, 5. So when x is 2 and y is 5. Now, if you wanted to verify this solution by solving the system using substitution, you could do that as well. I'm not going to take the time to do that here. Okay, here's another example. First equation is already set up in slope-intercept form, so we're going to start with plotting our y-intercept of -6. Now here my slope is -1, that's my slope. To make it have a rise and a run, I'm going to put it over 1. So from that point I plotted, I'm going to go down 1 and right 1. Or I could also go up 1, left 1, which is what I'm going to have to do for the vast majority of these, okay? I like to draw them nice and big so that I can see where these are going to intersect. Okay, let's take the second equation. On the second equation, we got to get y by itself. So I got to get this part by itself. So I'm going to first subtract x on both sides. That gives me negative 2y equals negative x minus 6. Then, to get y by itself, we're going to divide everything by negative 2. Pretend that's a negative 1 in front of the x. And now we get y equals, now when I divide two negatives, I'm going to get a positive 1/2 and then plus 3. All right, so just like on the first one, now I have it in slope-intercept form, so I'm going to plot my plus 3. And my slope, I'm going to rise 1 and run 2. And as you can see, that's taking me further away from the line, so I'm going to go down 1 and left 2. And I can see my intersection point. And now I'm ready to write my solution. My solution here will be negative 6, 0. Okay. All right. You could try this whiteboard problem out if you want. If you want to, just pause it, try them out. But I'm not going to give the answers to these, so we're not going to worry too much about this. You know what? Let's skip this example and this one. So let's just talk real quick. I alluded to this on Thursday in class, but special types of systems. There are two special types of systems. One would be no solutions, which would be graphs that never intersect. Okay, if we think about it graphically, they would have the same slope. So if I graph, two lines here that have no intersection, they would have the same rise over run. Okay, let's pretend that those have the same rise over run, but their y-intercepts, if I were to plot their y-intercepts, you would see one of them is up here and one of them's down here. So they'd have different y-intercepts. Algebraically, what that means is x's and y's cancel out. So if I were solving this algebraically, the x's and the y's cancel out, but I'd end up with a false statement. Okay, and we're going to see an example of this in a moment. Same on the infinitely many solutions. Infinitely many solutions just means you have one line, has some slope, rise over run. But then we have another line, which I'll graph in, let's do green, that has exactly the same slope and the same y-intercept. So like if I were to plot these on a coordinate grid, oops, that's ugly. You can, oh, that's not as better. Sorry. You can see they have the same slope and the same y-intercept. So same slope, same y-intercept. Algebraically, once again, the x's and the y's cancel out, but you have a true statement. So like 0 equals 0, or 5 equals 5, or it's probably most likely going to be 0 equals 0. And like on the false statement, you'd have 0 equals something else. Okay. And so now let's try an example. Let's say I had this system, and we've talked already about how to use elimination and substitution. So what would you use here? If you are like me, you'd probably use the elimination method. Probably going to eliminate. So now we have to pick a variable to eliminate. I'm going to choose to eliminate my x's. Well, in order to eliminate the x's, what can I multiply to 3 to make it a 6? If you said 2, you'd be right. I want to make that x a 6x. Okay, like so. My bottom equation, I don't need to do anything to it because I already have the negative 6x. And this is what I end up getting. So now we're going to add these equations together. This time you'll notice my x's cancel out, but oh my gosh, so do my y's. So that leaves me with 0. And if I do 20 plus 20, I get 40. So in this situation, we'd have no solution. And the reason being, this is a false statement. Okay? So we'd say there's no solution here. Okay? Let's try this example. If I look at this example, this time I don't even have to rename the equations because look what already happens to my x's and my y's. They both cancel out. So I get 0 equals, you know what, let's pretend this was a -7 for a moment, okay? So that gives me 0 equals 0. This is a true statement. And only because I changed that second 7 to a -7. Let's do that so that we have this example. Since 0 equals 0 is always true, we'd say that there are infinite solutions. Okay? And there you go. If I look at this one we would use our substitution method. And so for that, I would take this -5x plus 9, plug it into the second equation for y. And I'm just rewriting that second equation. Now let's see what happens. So we have 15x minus 15x, because I'm distributing that 3 to a -5x, which gives me -15x. And 3 times 9 gives me 27. Okay. Now if you look here, 15x minus 15x, those cancel out. Since those cancel out, that just gives me 27 equals 27. I guess this would be a situation where you would just have a true statement, but it doesn't have to be 0 equals 0. That is true, so we'd say infinite solutions. Okay? All right. Got it? Okay. You could try these out on your whiteboard if you'd like, but I'm not going to worry about it. And so now for the rest of this class, what I want you to do, there is no skill check to worry about here, so don't worry about that, but you are going to complete the IP for Unit 1.3. This will actually be due on January 23rd. That's just required by our e-learning virtual day. So I've made that due date the 23rd. Okay? Have a wonderful day and email me with questions.